In this video, we're going to derive the area formula for the area under a parametric curve from the formula that we know for computing the area under a function of the Cartesian form, y is a function of x. So if we just consider the situation on the right-hand side here, we have this function that's labeled y is a function of x. So this is not a parametric curve at this point. And if we're interested in the area underneath that function, between x equals a and x equals b, it is this shaded region that I'm highlighting now. And the nice thing for us at this junction is this is basically our old friend, the definite integral, where this was the integral from x equals a to x equals b of that function, capital F of x dx. So what we're going to do is take that idea of this definite integral written in the Cartesian y is a function of x form, so the non-parametric form, and we're going to mathematically massage that into the area formula for a parametric curve. And basically what we're going to do is a lot of substitution. And the first move that we're going to make as well, if this is in fact a parametric curve, what we want to do is define x as a function of t. So for example, if we consider this sort of in the parametric curve form, what that would have is we have x is some function of the parameter t. And we're going to make that direct substitution into this integral. So I have f, or capital F of, this little f of t. Now the next question that we have, because that capital F is now ultimately a function of the variable t, is we need to change what we're integrating with respect to. So we need to change that dx into something with respect to dt. And hopefully this feels familiar, just like for substitution with u substitution from earlier in the course. So we have this relationship, x is equal to this function of t. So what we actually do is take the derivative of x with respect to t, which in this case will be f prime of t, little f prime of t, and then we can go ahead and solve for that quantity dx up in that numerator. So if we solve for dx, what we find is dx is equal to f prime of t dt. And we're actually going to be able to move this directly into the integral now. So we'll actually have, this is capital F of little f of t times what we found coming from this derivative through this substitution, f prime of little t times dt. So now this entire integral is in terms of that parameter t. There's a couple things we still need to iron out though, those integration bounds, as well as what is this big capital F of little f of t thing. And well, if you remember from the beginning of the problem, we called y that function of x. So actually this here is nothing but y of t. So this integral is looking like the following. So before we look at the bounds, what this integral is looking like is the area is equal to this integral, which we're going to put stuff in the bounds in a moment. So I'll just kind of highlight that we still need bounds up above. We have the function y of t, which is our parameter coordinate function for y of the parameter t. We multiply that by the derivative of the x coordinate function. So this here is actually little f of t, or little f of f prime of t, is actually x prime of t dt. So again, just so we're on the same page, that y of t was our original capital F of little f of t. And this infinitesimal quantity that we substituted from dx, that was our original dx that we could write through that u substitution as f prime of t dt. So that's where all of these characters from the integral are coming from. And the last thing we need to figure out is, well, what are the bounds? And the bounds, actually, the way in which we compute these is very geometric. So we're considering the bounds from earlier, x is equal to a and x is equal to b. So what this tells us is we're looking for specific values of x, of a and b. So we can take our x equation. So remember our x equation, which was x is equal to f of t. And what we need to do is substitute in those values for x and solve for the corresponding t values. So what we need to do is solve the two following equations. We need to solve when x is equal to a, that's equal to our function of t. And we need to solve the second when x is equal to this number b, that's equal to our function of t for the x coordinate. And we need to solve for the t values that will land us at those specific x values. So we're really solving this kind of for the t now, because we know what a and b are, but we need to figure out what t value puts us at that specific location along the curve when x is equal to those values. So in this case, what I will just say is, let's just assume for a moment that the following happens, that when t is equal to alpha, that is when x is equal to a. And when t is equal to beta, that is when x is equal to b. So again, what we're basically assuming here is f of alpha is equal to a, and we're assuming that f of beta is equal to b. Just to make sure we're on the same page. We solved when x is equal to a, we solve for that t value, we solve for the t value that lands us when at the point x equals b. So if we take those ideas and we blend them into our integral formula, what this tells us is our integral runs from the lower bound of t equals alpha to the upper bound of t equals beta of whatever function we're given for y in our parametric curve times the derivative of our x coordinate function with respect to t dt. And that is our area formula for the area underneath a parametric curve. So let's actually go ahead and try to apply this to an example right off the bat. So the example I want us to look at is to find the area under one arch of the following parametric curve, when x is equal to t minus sine t, and when y is equal to 1 minus cosine of t. So this is our parametric curve. And just so we're on the same page, we're interested in finding the area under one of these arches. And the other thing I will just say, this type of function actually, or this parametric curve has a special name. This is called a cycloid. So it'll actually continue this arch pattern for all t values over and over. So let's see what we need for this area formula. So remember, we had this area formula, which was for some lower t bound, which I think we just called alpha before, and for some upper t bound, which we called beta, and we needed y of t times the derivative of x with respect to t dt. So right away, we can start plugging in some of those quantities. Since we know what y is, in our equation above, we know y of t is 1 minus cosine of t. And we know what x of t is, so we can take a derivative of x of t, and that will give us a 1 minus cosine of t. And that's still an integral with respect to dt. So just we're on the same page, that first 1 minus y of t, that's just the function y of t from up above. And that second one is the derivative of our x coordinate function, x prime of t in this case. So the thing we still need to figure out though are, what are those upper and lower bounds for this specific integral? In this case, we are told we want to find the area under one arch of this cycloid or this specific parametric curve, which corresponds, we could just choose, say, this arch in general. And what we need then is we need to find the point in which we start and the point in which that arc ends. So a couple things about those points that we can recognize. We know that at this first point, x is equal to 0 because we're at the origin, and we also know that y is equal to 0. What we immediately know about this next point is we know at y is equal to 0 at the second point. X could still be equal to a number of things. We're just going to need to figure that out. So the first thing it looks like we should be doing is finding values when y equals 0, since y equals 0 appears to be kind of synonymous between both of those points. So we're going to find t values such that y is equal to 0. And then we're going to compare those, and you look at the x values at those specific t values as well. All right, so if you remember our function for y in this case was equal to 1 minus cosine of t. So what we're interested in is looking at values of y where y is equal to 0. So we're actually going to take our equation for y and just set it equal to 0. Because again, at both of those points, we know y is equal to 0. So it looks like what we need to solve is the equation 1 minus cosine is equal to 0, or basically that 1 is equal to the cosine of t. So what t values will actually land us at these points? Well, let's take a couple looks. So basically we know that cosine is equal to 1 at multiples of 2 pi. So we can actually find that t is equal to 0 will satisfy that equation. T is equal to 2 pi, t is equal to 4 pi, t is equal to 6 pi, and so on and so forth. The other thing that we can get, though, is not only is t equal to those positive numbers that land us at values of cosine being 1, but also their negative counterparts. So if t was either plus or minus 2 pi, plus or minus 4 pi, plus or minus 6 pi, we would always get values of the cosine equaling 1. All right, so it looks like we have a bunch of candidates now for successive points that would land us at y equals 0. So which ones are actually going to land us at, say, the first point and, say, the second point? So this is where we take the x equation and we start thinking about what values of t, or what happens at those specific values of t. So if you remember, our x equation from up above was t minus sine of t. And well, since we're interested in just the area under one of these arcs, basically it might make sense just to use two t values in succession. So what I mean by this is we could use values like t equals 0, and then the next t value after that would be t equals 2 pi, and after that would be t equals 4 pi, 6 pi, and so on. We're basically looking for these t values that land us at y equals 0 in a row. So what happens at t equals 0? So if we evaluate our function x at t equals 0, what we get is 0 minus sine of 0, which is equal to 0. So what this actually says is, this is an x equals 0 when t equals 0. So what it looks like this first point is associated with t equals 0, since both x and y are equal to 0 when t is 0. So let's try the next value of t. And this could be t is equal to 2 pi. So if we put 2 pi into our x equation, we will get 2 pi minus sine of 2 pi. And well, the sine of 2 pi is 0. So it looks like that x value at the next t, or when t is 2 pi, x is actually equal to 2 pi itself. So up here, when we didn't know what x was equal to, it turns out that x is equal to 2 pi at this point. And this is also corresponding to the point t is equal to 2 pi itself. So remember, we basically asked ourselves, we know something about those points. We know their y values. How by finding the y values can we get the t values associated with those specific values of y? And then we just said, what do the x values look like at some of those t values to make sure we're thinking we're at the points we are along that particular parametric curve. So what this helps us do is then figure out what these remaining bounds of our integral are. We're rolling for the integral from t equals 0, then to t equals 2 pi. So the last thing for us to do is inside of this integral, put on the bounds, t equals 0 to t equals 2 pi. So I'm just going to go ahead and grab this integral and carry it down below for us to compute it. All right, so remember, this was our area integral under one arc of that cycloid. All right, so I'm just going to get rid of some of these function definitions from up above. And we just at this point have a definite integral to actually compute. So in this case, the full integrands in terms of t, our bounds are in terms of t. Let's go forward and integrate this. So the area is equal to, from t equals 0 to t equals 2 pi. First thing I'm going to do is just distribute this right-hand side. So get 1 minus 2 cosine of t plus cosine squared of t. Now, two of these terms, I would argue, we can actually integrate mostly straight away. We can integrate this constant 1 and this minus cosine of 2t. But this last term on the integral, we get to do a little bit of work on that. So remember, whenever we had sine squared or cosine squared only terms, we used our half angle identities. So we're going to make the substitution in a moment into the integral using this half angle identity, that cosine squared of t is 1/2, 1 plus the cosine of 2t. Let's go ahead and just make that substitution. So this area integral is still the area, or the integral t equals 0, t equals 2 pi, 1 minus 2 cosine of t, plus, and then we're just going to put in that half angle identity. 1/2 times 1 plus cosine of 2t. Now we can actually go ahead and, in a straightforward manner, kind of integrate this. Actually, you know what? Before we integrate, let's just kind of tidy up what we have so far. So just looking at this, we'll distribute this 1/2 into each of these terms inside the square brackets. Ultimately, we'll get a factor of plus 1/2, which we can combine with that 1 that's sitting out in front. So this will give us a factor of 3/2. Then we have minus 2 cosine of t. And then we have this factor of plus 1/2 cosine of 2t. And now we can compute those antiderivatives. So this area now is equal to the antiderivatives before they're evaluated at the bounds, 3/2 t minus 2 sine of t plus 1/4 the sine of 2t. And we have to remember to evaluate at those bounds, t equals 0 and t equals 2 pi. So if we plug in those bounds, we will get the following. So plugging in the top upper bound first, we have 3/2 times 2 pi minus sine of 2 pi plus 1/4 sine of, in this case, 2 times 2 pi. And then we subtract from that the antiderivative evaluated at the lower bound, which in this case will be 3/2 times 0 minus 2 times sine of 0 plus 1/4, ultimately sine of 2 times 0. All right, let's see what happens. Just looking at what we have here, we have lots of sines of 2 pi, sines of 0 as well. Sine of 2 pi is equal to 0. Sine of 4 pi ultimately is equal to 0. 3/2 times 0 is 0. Sine of 0 is 0. And lastly, I guess we still have another sine of 0. So the only thing left, it turns out, is that the area of one arc underneath the cycloid, or the area under one arc of this cycloid, is equal to 3/2 times 2 pi, or 3 pi. So remember, the big idea for this example and for what we're doing is basically we converted what we knew about a definite integral that gave us the area under a function between a certain x point and another x point. We converted that into the parametric form. So our area integral in parametrized curves is between some lower t value that we just called alpha generally before, to some upper t value that we call beta, of whatever our parametric coordinate y function is, times the derivative of our x function with respect to t, dt. So this was our area under a parametric curve that we found.